Hi students, in this video we are going to study our third unit, which consists of three chapters like dielectric materials, magnetic materials and nanomaterials. So today we are going to discuss about dielectric materials. So let us see what is the dielectric material and its properties. Okay, so dielectrics are insulating materials. So there are no free charge carriers in them. So whenever the insulating material that it is, that means there is no charge carriers for carrying the charge. That is, in dielectrics, all the electrons are bound to their parent molecules. Even with normal voltage or thermal energy, electrons are not released. Dielectrics are non-metallic materials of high specific resistance and have negative temperature coefficient of resistance. So these are non-metallic materials which are act as insulating materials of high specific resistance and have negative temperature coefficient of resistance. We know what is meant by conductance, what is meant by resistance. Okay, all these terms. Dielectrics have permanent electric dipole moment. That means dipole means which are having two charges. Those are two equal and opposite charges. So the dielectrics have permanent electric dipole moment. Dielectrics are mainly used to store electrical energy. So examples are rubber, glass, plastic, mica. Okay. So when dielectric is placed in an electric field, then separation of positive and negative charges takes place, causing polarization of the dielectric. So whenever we are by using an electric field, we are separating the charges inside a material that undergoes a polarization of dielectric material. So in this, when dielectric material is placed in an electric field, then the separation of positive and negative charges takes place, causing polarization of the dielectric. So the dielectrics are of two types: polar dielectric materials and non-polar dielectric materials. So see here in the first diagram there is no field, and in the second diagram electric field is on, the separation starts. So whenever no electric field, the polar molecules, so non-polar molecules are like this and the polar molecules. Okay, and next, polar and non-polar dielectric materials. In non-polar dielectric materials, the molecules are usually diatomic and composed of same type of atoms. Okay, so whenever we are taking the non-polar dielectric materials, the molecules are usually, those are said to be diatomic and composed of same type of atoms. In case of non-polar dielectric, the centers of both positive as well as negative charges coincide. So the dipole moment of each molecule in non-polar system is 0. So all those molecules which belong to this category are symmetric in nature. So example for non-polar dielectric materials are, so like the H2, N2O2, C6H6, C6H4. See how a non-polar molecules will be with field or without field. Okay. And next, polar dielectric molecules. So polar dielectric molecules are normally composed of two or more different types of atoms. So polar dielectrics are those in which the possibility of center coinciding of the positive as well as negative. That means all the polar molecules which are present in the dielectrics, those are coinciding of the positive as well as negative charges, that is almost 0. That means what happens means they do not coincide with each other. The reason behind this is their shape. Due to their shape, they will not coincide. They all are of asymmetric shape. Okay, and examples of polar dielectrics is NH3, HCl, CH3Cl, H2O, etc. Okay, and now, so before going to this chapter, we have to study some definitions. So what are those? Let me explain. Dipole, a system consisting of two equal and opposite charges separated by a small distance. Dipole moment, it is the measure of the polarity of the system. Okay, dipole means having the two equal and opposite charges separated by a small distance, and dipole moment means it is the measure of the polarity of the system. So the product of one of the charge and distance between two charges is called dipole moment. So the product of one of the charge and distance between two charges is called a dipole moment. Now dipole moment mu equals to qd, units coulomb meters, means here P is one charge and Q is the another charge, and separation distance between two opposite charges is D. Okay, so we are considering the dipole moment as mu. Let it be the product of any one of the charges to the distance between the two dipoles. Okay, so P equals to QD. And next, electric polarization. We already studied the concept of polarization. Now we have to study what is the electric polarization. So the process of producing electric dipoles by an electric field is called polarization in dielectrics. I will repeat it again. The process of producing electric dipoles by an electric field is called polarization in dielectrics. Okay, we are separating the charges. We are separating the dipoles by using a field. Okay, and next, polarizability. The induced dipole moment per unit electric field is called polarizability. Induced dipole moment by electric field, that means unit electric field, is called polarizability. The induced dipole moment is proportional to the intensity of the electric field. That is, we are considering the dipole moment as mu and electric field E. Those are proportional to each other. So mu equals to alpha into E, where alpha is polarizability constant. So here we are describing the alpha is a coefficient of polarizability. So, okay, so alpha is a polarizability constant. And next, permittivity. Permittivity is let it be denoted as epsilon. Now the permittivity is a quantity which represents the dielectric property of a medium. It indicates the easily polarizable nature of the dielectric material. So repeat it again. Permittivity is a quantity which represents the dielectric property of a medium, and it indicates the easily polarizable nature of the dielectric material, and the units for permittivity is Faraday per meter. Okay, and next, free space permittivity, epsilon naught, that is the permittivity of free space or free space permittivity. It represents the capability of a vacuum to permit electric fields. It is also connected to the energy stored within an electric field and capacitance. So it is a constant value for permittivity of free space, that is epsilon naught equals to 8.85 into 10 power minus 12 Faraday per meter. Next, relative permittivity or dielectric constant. So we already studied permittivity and permittivity of free space, and now studying relative permittivity. Let us see what is the difference. So the dielectric constant is the ratio between the permittivity of medium to permittivity of free space. So relative permittivity epsilon r equals to epsilon, the ratio between permittivity epsilon by the permittivity of free space epsilon naught. Now the characteristics of a dielectric material are determined by the dielectric constant and it has no units. So what are the characteristics for a dielectric materials? Those all are determined by the dielectric constant and it has no units because it is the ratio. The units gets cancelled. And next, polarization vector. The dipole moment per unit volume of the dielectric material is known as polarization vector. So we all know the polarization and dielectric polarization. Now what is meant by polarization vector? So the dipole moment per unit volume of the dielectric material is called polarization vector. So that is P equals to N into mu. Okay, Coulomb per meter square. Next, electric flux density. Let us see. The electric flux density is a measure of the strength of an electric field generated by a free electric charge. So it is the measure of the strength of the electric field that generated by a free electric charge and corresponding to the number of electric lines of force passing through a given area. That is known as the electric flux density. And it is the amount of flux passing through a defined area, specified area that is perpendicular to the direction of the flux. How many magnetic lines that how many electric field lines will pass through the given flux. So that is said to be a electric flux density. Units as a coulomb per meter square. Okay, and next, electric flux density D at a point in a free space or air in terms of electric field strength is D equals to epsilon naught E. Okay, here epsilon naught is a permittivity of free space, and at the same time in the medium is given by D equals to epsilon into E. So whenever it is considering in a free space, it is D equals to epsilon naught E. Within a medium, D equals to epsilon E. Next, the flux density at point free space, we know that, and as the polarization measures the additional flux density arising from the presence of material as compared to the free space. So here is a polarization vector concept arises. So the polarization measures the additional flux density arising from the presence of material as compared to the free space, that D equals to epsilon naught E plus polarization rate. So from these equations we know that epsilon E equals to epsilon naught E plus P. So now P equals to epsilon minus epsilon naught into E. Okay, now we are replacing this term into the permittivity. That means, what is the term? Relative permittivity. So from this we are replacing this epsilon value, and by taking the common value epsilon naught, P equals to epsilon naught into epsilon r minus 1 into E. So we can relating all the definitions. Okay, and next, electric susceptibility. The electric susceptibility is a dimensionless proportionality constant that indicates the degree of polarization of a dielectric material in response to an applied electric field. So whenever we are applying some field, it indicates that the degree of polarization for a particular dielectric material. It is defined as the ratio of polarization vector to the applied electric field. So susceptibility xi equals to P by E or xi equals to P by epsilon naught into E. So that is represents as permittivity of free space. So P equals to xi epsilon naught E, and here also we are replacing the term. Okay, we know that because from this equation. Okay. So these are the basic definitions in this chapter. So next we are going to study with the types of polarization.